Okay, the first question on the document for today was parallel circuit. You have a nichrome wire of double the length of another nichrome wire, those two wires being in parallel with a single source. The wires have the same diameter, so the only difference is the length, this one being double this. So the question, two questions, what is the ratio of the voltages V2 over V1? What's the ratio of the currents I2 over I1? You should think that through. If you've seen my answer here, you should justify it without reading. You should think this through if you weren't in class. So what should the ratio of the voltages be? What should the ratio of the currents be, and why? Now, hopefully you paused and done that if you weren't in class, or if you're still trying to get your head around this stuff even if you were in class. Well, in the first place, the two voltages are equal. And the reason for that is there's a direct path through a conductor from this wire to the meter, or to the source, and from this wire to the source. On both sides, you have direct paths, so both wires are experiencing the same voltage, so that V2 over V1 is 1. Okay? Now, what about I2 over I1? Okay, well, yeah, again, you want to think that through if you haven't already, but I'm going to go on now. Okay, we got an answer 1 to 2 or 2 to 1. And I didn't specify if it was a ratio of this one to this one or this one to this one. So either of those, if 2 to 1 is right, then 1 to 2 could also be right, because we're not being specific about which is which. But which of the two, well, the question is not so much which, but the question is, why would you have a 1 to 2 or 2 to 1 ratio of the currents? Well, you're familiar with what happens when you crank the generator. You have less force, indicating less current on a longer wire. Okay, well, this wire is twice as long as this one. Why is it that would give you a 2 to 1 or a 1 to 2 ratio? You would have twice as much current here as you would have here. Okay, so it would be 2 to 1, or you say 1 to 2, either way. So I asked why, and somebody came up, well, V equals IR. And that leads you to the conclusion, if you understand that this wire has twice the resistance of this wire. Okay, now we haven't completely established, though, that twice the length should have twice the resistance. We know it has more resistance, but is it twice? Well, we have kind of established that, because we've talked about the fact that if you have a longer, well, first of all, it was observed the longer wire has more resistance. That's a good answer. But why isn't there more resistance? There's more resistance because the electric field is less. Okay? The electric field is your voltage change divided by the distance over which that voltage changes. And it's uniform for a uniform wire. So that delta V over L is less if L is greater. So this is less for greater L. Now, don't confuse my use of the term L down here with the more specific L and 2L we had up here. That just means intuitively, and you should understand this, that the longer wire spreads the voltage out over a greater distance, and the spread of the voltage in a uniform wire is a measure of the electric field. And you know the work and energy relationships between voltage, field, and distance. Or you should, because that's what you need in order to do this. Okay? And in that case, if L is twice as great, then you do get half the electric field, which gives you half the acceleration of the electrons, and therefore twice the resistance to the flow of the electrons. If you've got less acceleration, then the electrons drift more slowly. The net drift of the electron cloud, or whatever you want to call it, is slower. Okay, well, Here's another situation. We have two voltages, but they're in series. So we have nichrome twice the length here compared to the length here. This has twice the length of this one. And they're connected by conductor and in series with a voltage again. So the question is, what's the ratio of the voltages? What's the ratio of the currents? Again, they should think through that. Okay, well, the main thing, the thing that should be really obvious here is that the voltages have to be the same. The thing that should be really obvious here is the currents have to be the same. The charge has no place to accumulate. So any charge that passes through here also has to pass through here, and also through the source. So that the current is the same in both, so the ratio of the currents is 1. Charge can't build in this circuit. If we had a capacitor in there, charge could build, and that might change our thinking, might not, in answer to this question. Okay, now what about voltages? Well, somebody quoted V equals IR, and this V equals IR follows directly from this electric field calculation and so forth, and other considerations, things that we've talked about already. So we know that. So we could go ahead and cut to that for right now without going into a more basic fundamental explanation. You have the same current, so we just call that current I. So V2 is I times R2, V1 is I times R1. Okay? So if R2 is the resistance in the longer wire, then the ratio would be 2. Okay, because R2 would be twice as great as R1. If it's the opposite, if you think R2 is this one, and of course I call that V2, then that's going to have half of the voltage of this one, and you would have ratio 1/2. The whole point is that the longer wire, longer wire has, the double length of wire does have double the resistance because of what we said here. And constant current means that you have twice the voltage drop through the wire of twice the length. Okay, and over here again, same voltage drop through both wires gives you the current ratio.